To explain, I got a lot of the many students contact me. They're gonna have a difficult time to what is the decide the topic for exam one. So I will looking explain how to get um, how to find the papers. Let me share my screen first. Yeah, if you are going to Google and go to Google Scholar first. Once you get a Google Scholar, just type uh, more circles. Let me double check. I made a lot of time the typo. So copy and paste. And then once you search it, you can get the lot of the papers and just click one of them. At the time, I think it did most of all calculation. Calculation. Then you there's a lot of papers. They're gonna let many researchers or scientists already studied, and just click one of them. At the time, you are the kinds of the paper they did before, and they provide how to establish the most circles like that. And then let me show the another papers. Yeah, if you see it, you can see the most circle data, right? So just click it, and then once you uh, just search the papers in using the Google Scholar, you can get the reference paper. Also, I would like to explain this one. If you see it, then I think it is not good examples. Let me see. Mm, this one. Okay. So just to review. Oh, okay. Yeah, okay, this is a good example. They're gonna provide the kinds of the metrics of the uh, stress and strain. Then they calculated the most circles, strain most circle and stress most circle. Uh, yeah, so this is one of the good examples. But I would like to explain another one is, mm, yeah, this one. I think the university usually only make the contract with a few journals. So if you use the university of Missouri, uh, the internet university of Missouri, you can download it, the papers, these journals uh, make a contract with the university of Missouri. But in this journal, they didn't have the they didn't make the contract with University of Missouri. So at the time, you need to contact the library and ask you, I want to see these papers. It may take quite a long time. So please use the SCI Hub. SCI Hub. At the time, just just try to find the DOI on copy onto this part. Don't copy DOI.org. Only copy this part and paste. Then click it. At the time, you can get the papers. I'm not sure this is a recipe, most circle or not, but I think it's related. So, I think when you search the papers in your house or in your home, I think since you use your the home internet service, you cannot download the papers. At the time, you can use this one and then type the DOI, and then you can get the papers. So, but another way is you download the Cisco any connect, then and then if you use this one, you can use the universal media connections. Even if you use even if you try to find the papers in your home, but if Universal Missouri didn't make didn't make a contract with some of the journals, I think it will work. So I suggest just to use the SCI Hub. This is better than SCI Hub. Okay. So I will extend the topic selection due until this Thursday. So I try to encourage you guys select the topic yourself, because you can get the 5 points. Okay, let me start today's lecture. And I'm really sorry I missed the last two lectures, but and then last week I made a mistake when I saw the this one, these examples. Please double check. I made a mistake here, so please revise your solution. I made a mistake. So at the time, we get this value, and we can calculate it, sigma. There's stress 1, stress 2, and stress 3. And then, according to the stress 1 and stress 2, stress 3, and 3, we can calculate it. RMN is related to the cosine zeta, zeta 1, zeta 2, zeta 3. Okay, let's move on the strain. In fact, we can also make it a strain most circles. As we okay, as we see that this reference paper provides stress, strain, most circles. So like that, we can calculate just most circle per stress. If we assume there is the load and direction in y directions, the deformation could happen at the time the point A is moved to point A prime, point B moved to point B prime, and point C moved to point C prime, and we can make it a displacement. There is a lot of the displacement procedures. Sometimes There's a translational displacement and rotational displacement and just the shear displacement. Translational displacement is they're gonna change its position on position. So as you can see, there is no shape change, but there is some of the position changes. Rotation is you already know the what is the shape could be rotated based on the standard positions. At the time, you can get the rotations angles set up. If we consider shears, that there is the shape changes. You can see shape could be changed. So we can if we just assume the shape these materials has a lot of particles, and particle has the own vectors, position vectors. So this is the A, and this is the if we apply the force, A is root A prime. At the time, we can use the U with W to explain the position change of X, Y, G. So we can make a correlation. X is expressed to X plus U, Y is moved to Y plus V, Z is moved to Z plus W. So we can make it a displacement vectors. It is called is raised to U V W. So U V W is translational units on X Y Z axis. So um, so we can explain displacement is equals to translational, rotation, and shear as I explained before. So we can explain the translation displacement vectors. Next. So just first, we are going to think about the 1D linear strain case. And so if we just think about here is some of the load, and is we assume just there is the surface. Let me make it clear. Right. And there's one more point. This is E. A. A. So we will go and then make line factory. Then if we apply the force like this question, and increase like that. At the time, it is moved to look here, but it is moved here. So A is, if we assume this distance is U, we can explain this distance by U cross Do you understand? And then it is easy to convert like this thing. So uh, we can make it a relation. Yeah. So based on
Sorry,
the
I have a question. So what distance of the dirty U?
which one?
What's the distance of dirty U?
This one?
Yeah.
Oh, it depends on your the materials or any other your experiment. This is just a definition how to make it a relation.
Okay.
It could be changed. Delta U always change it according to the material type. In case of the metal or in case of ceramic material, it's quite low, but in case of the rubber, it's extremely high.
Okay. Thank you.
Mhm. And then we can make based on the definition of the strain. Thank you for your question. Yeah, it's a very good question. And then, based on the definition of the strain, we can make a relation of the distance between the AB and extended A prime and B prime. So based on the definition of the strain, A prime B prime distance minus AB distance divided by AB is expressed by like that. So this is a, if we assume this is a dx, we can describe the A prime B prime distance as dx cross boundary u round x and dx. And AB distance is a dx. So it is exactly the same. So we can get this relation. Also, um, if we integrated this relation, we can get this one. U equal U0 plus uh, this and X. This is kind of the linear relations. Then, if we just assume this is a rigid body translationals, we can say the U equal EXXX. It means just the U is zero. U0 is zero in this case. Do you understand? Is there any questions? Okay, move on the 103B. Um, if we what is the stretch is something or apply the force, material could be stretched or extended at that time. In the 3D case, what is the U is related to the X direction force, Y direction force, and G direction force. And V direction change also related to the X direction, Y direction, G direction. W is the G direction deformations. It is also related to the G direction, the X direction, Y direction, and G direction force. So according to the, if we assume, if we consider every component, we can make it a normal linear stress relation like that. So EXX expressed by round U round X, EYY round U round Y, BZZ is round W round V. Is receive the delta U over delta X, delta V over delta Y, delta W over delta Z. Uh, Yeah, I already explained it. If we apply if we apply the x direction force at the time, we can get uh, the x or y or z direction displacement like that. So in this case, we can explain the x direction displacement is u, y direction displacement is v, and z direction is w. So just think about x, y. So if we make it the y direction distortion, might make the y direction force, at the time it is related to the d prime is the d prime is a is d prime is part d prime, and since we apply the force by the y direction, it is this direction, I think. Yeah, this direction. No? Anyway, I think this direction. Let me double check it. But this direction. So
Shouldn't it point upwards? Because in
I
the previous slide I saw that.
can you say again?
In the previous slide, I thought the load was on the upward, on the y direction, positive y direction.
This one. Okay. Let me explain this one again. This part later. This is the direction how to define the negative value and positive value of what is a displacement strength. Yeah. Just don't think about this in this step. So is the shear distortion of the y-axis in the x direction is defined by exy, and it is related to delta over h. It means if we apply what is a y direction distortion, make it y direction distortion as the h, the x direction distortion could be appeared like dd as dd, right? dd distortion displacement. So we can define around the du over dy. It is or delta u over delta y. Oh, it is y and x is eyx mean is if there is a distortion of the x-axis, and we can see the distortion of the x-axis. So if we apply the y direction distortion. Oh, no. Yeah. It is correct. The y direction distortion, if we apply the x direction force, if we apply the y direction force, and at the time, we just focus on the y direction distortions. So it is related to describe as delta v over delta y.
I have a question.
So,
What is the third and H?
now delta H, if we apply the this one. So if we apply the force as the direction, this direction, what is this? That at the time, the H is the change the point of this direction. Um, 30 here. H here. And D is delta is they're gonna decrease from here. This direction is defined delta. This one. Do you understand?
So the dirt is the horizontal change, and the H is a vertical.
Oh no. H is related related to the direction of H is related
Or it's just the
applied
original length of
applied
the...
load or force direction. It means y direction change if since we apply the y direction force, we consider this direction displacement is h. Do you understand?
Okay, but then what is why is the H is equal to dA in the first equation?
Since we apply the y direction force, the force is applied like that. So we consider the A direction, the dA.
Okay, I understand. Thank you.
Thanks. And then delta is related the what's the x direction distortion. Then it is related to the displacement strain. But the important thing is the notation. So if we just think about if we just EIJ, the first one I is direction of the displacement. The direction of the displacement. J is the plane on which strain acts. So in case EXX, in case of EXX, displacement direction would constant x, and strain could act as x direction. Then EYX is y direction displacement, but the strain act as x direction. Do you understand? I think I made a confusion when I used the force or stress directions. Just don't think about just I would like to explain if the force applied the x direction, the strain could happen x direction. So I use the strain term to understand more easier, but it can make confusion. X direction strain, X. Yeah. So, and then in case of EZY, EXY, the strain, the displacement could happen X direction, but strain can act by Y direction. So this is a deep displacement to the positions. And then convention is the sign positive is positive mean is IJs are positive. Do you understand? Or IJ are negative.
So the
If they have
strains
this,
on the negative faces will be equal?
yes, negative phase has them positive. But if
The
they
plane on the
have
left side, sorry, the plane on the left side, if you look at the direction on the X, so, yeah, that where your pointer is right now, yeah, that one, what would that plane would be?
this is the downside is E, the downside is GY, and it is EYY, and size is EXY.
But that isn't the plane on which the strain acts, right?
Yes, because so we call this is a positive phase. This phase is negative phase. And this one is also has a different axis, EZZ, and its negative is ECZ.
Oh, so the opposite side would be the negative
Yes,
one.
yes.
Okay.
We call the negative phase, or we call it positive phase.
Okay.
Because what is if we apply the tensions, the force direction could happen like that. And then this phase would happen force apply like that. So it's the opposite direction, right? So to explain this phenomenon, they're gonna have the different phase. Is a positive phase, positive phase, positive phase, and the negative phase, negative phase, negative phase. Think it is related to your previous lecture, I think. Yeah, here. It is the same to the stress tensor, I think. You see that this one, they have the different stress and shear stress and normal stress. Shear stress and normal stress right there. So they're gonna have the same rotation or directions. Then okay. So we can express the 3D displacement strain matrix as the XX, XY, EXG, and 9 component EYX, EYY, EYZ, EZX, EZY, and EZZ. So it is all related to the deceleration. And then they're gonna produce the shear strain with various rotations. So if we consider the rotation, shear rotation like it. If we think, if we assume EXY equal to EYX, do you understand? So EXY change is equal to EYX. This change and this change is the same. They're gonna, you can at the time you can assume EXY equal EYX. But if there is a rotation like theta, EXY equal minus EYX. This is minus EYX, negative value. And then if we consider just a simple shear, EXY is delta U over delta Y, but EYX equals 0. So we can think about the three cases. This is shear without rotation, and simple shear displacement. So we can decompose the strain. The EIJ is the shear strain and WIJ is related to the rotation. This is the shear without rotation. This is the rotation. At the time, we can just assume EIJ, WIJ is decomposed to EIJ, EJI, and EIJ minus EJI. So this part is symmetric shear, this part is antisymmetric rotation. And it could decompose some of the strain. So we can explain the all displacement strain is equal to the shear strain tensor and rotation tensor. The shear strain tensor could be explained by like that. The EXX, EXY, EXZ, the EXX half of the EXY plus EYX, half EXZ, EZX. So we can get this relation. But in this rotation tensor, the EXX, EYY, and EZZ is 0, and then we can obtain this component for WXY, WXZ, WYZ, WYX, WZX, WZY. And the sum of the two tensors, just strain tensor and potential tensor, is related to the displacement strain matrix. So EXY plus EYX is equal to the 2 epsilon x, to XY without the shear strain, without rotation. It is directly related to engineering shear strain. Do you understand? So we can express the gamma xy equal to around u over around y, around v over around x, is gamma c is equal to the around w over around x plus around u over around v, and y gamma y z equals w over around y plus around v over around v. So we can understand the total angular change from the angles. Do you understand? Do you have any issues about the stress tensor, shear strength tensor, and rotation tensor? Okay, so we can convert it to this equation. Do you understand? Do you remember these equations? We got this equation from the last lecture. When we to the when we solve the like this kinds of the this equation. Actually, where is this this one? This equation. So using I couldn't find it like okay. So we can replace the epsilon sigma and one over two tau. So we have the deceleration before, then the stress tensor and normal stress and shear stress and strain. Then at the time we can calculate it like deceleration. So do you remember the last example problem? We got these relations, and then we put this number from the matrix. Then we can calculate it I1, we can calculate the I1, I2, I3 first. Then we calculated but at the time we calculated, I think it's normal stress 1, normal stress 2, and normal stress 2. Similar to this case, we can calculate the strain 1, strain 2, and strain 3, displacement 1 to 3. So to calculate the strain 1 and strain 2 and strain 3, we can solve this relation first. Then we calculated, we gather the three kinds of the relation, three equations. Then once we gather the strain 1, strain 2, strain 3, strength 1, strength 2, strength 3 is directly related to the RMN. Do you understand? Let me double check the last examples. we have this normal stress data. At that time, we have the normal stress 1, normal stress 2, normal stress 3. Each normal stress has a L, M, N. It is directly related to the three equations based on the what is based on this relation. Exactly same to the string. So if you calculate the string 1, string 2, string 3, we can directly make the correlation with the L and N. Do you understand that? So we can solve the problem like the previous examples. Since we have the three string 1, string 2, string 3, we have the maximum displacement. So means A, then is the related to string 1 minus string 3. We can say this is a maximum displacement. Honestly, previously when I saw the problem, I assumed the volume would not be changed, and then I calculated the stress and strain. But in fact, in their system, the volume could be changed. So to consider the volume change effect, we can use this relation. So just assume the length of the cube is dx, dy, dz. At the time, volume is directly calculated by dx, dy, dz. And then volume of strange element could be if we make this if the what is the cube what is the deformed, we can calculate the volume of this one by these relations based on the definition. Do you understand? Okay. And then the volume strain could be its volume strain could be expressed by like that based on the same definition of the strain. You already know the definition of the strain is the delta L over L is exactly the same. Volume strain could be expressed by the volume change over initial volume. It is the volume changes change and initial volume. Do you understand? So it could be expressed by the if we solve this one, we can say sorry, just to simplify. See this one. So we got a simplification now. So we can, if we neglect the product with this one, just this one, just this one, this one, we can simplify the volume strength would be expressed by like this. Do you understand? Do you understand how to change it from this one to this one. Should I drive this equation? I think you can. So what is the if we just focus on the string xx, string xx, string yy is neglected. So we don't think about string xx 1 then y 1 then zz 1. So we get just this. Then -1 from okay. Then so we can calculate the height of the mean strain. Mean strain is just there is a 3 component. We can calculate the mean easily. So but this strain cannot make the shape changes because it is related to the x direction. X displacement is related to the x direction swing, and y direction displacement related to the y direction swing, and g direction displacement according to the g directional swing. So they cannot make it shape changes. But it causes volume changes. Like that. So it is called hydrostatic component. Hydrostatic component. So we get the kind of the part what is the it can affect the shape changes called strain deviator. Strain deviator. So then we get the strain deviator by subtracting the mean strain from the normal strain component, like that. Do you understand? Usually the shape change could be, the volume change could be related to this same direction, what is the same direction displacement. Just like it. And so the strain deviator could express by writing. Then based on the what is the definition of this one, we can express the what is the strain deviator like this relation. Do you understand? Okay. And then finally we got the distributions based on the this matrix. Sorry. Okay. Finally, we also created a Morse circle for strain, which we showed the first paper like that. So Morse circle of the strain can be expressed by like this is the maximum strain. This is the what is the minimum strength. Then we can explain the what is the strength about the according to the theta. Are you okay? So the theta max, not theta max, the string max and string mean is directly related to the solution of the uh, solution of the in case of 2D, this is a two order equation. So this is kind of the root of the equations. So plus is related to the string max, minus is related to the minimum. The max is also related to the kind of the radius of this circles. So we can calculate the diameter like it based on the circle equations. And tangent to theta is normal stress at the time is related to the x over strain xx minus strain yy. I think we can tangent to theta. Anyway, I didn't. Okay. Then in case the shear is minus negative strain xx minus strain yy over my xy. I think so. There is the kinds of the strain measurement. So it's a rectangular shape or delta shape. According to the measurement, we need to consider what is the angles. Then you can make it a relation between you can consider the angle effect. So, what is the string? I think it's a kind of the string measurement method. So we can, but I would like to explain. Stress is related to the sigma 1 sigma 1 2 sigma 1 3 sigma 2 1 sigma 2 2 sigma 2 3 sigma 31 32 33 33. But the strain is expressed by like it's very same, it's exactly same. But if we study the more complicated tensor, we usually use the different notation to simplify the tensor. At the time, we just use xx is 1, 1, and then we can say this is 1. Y is, we can say is, I think it's 2, 2. But it's, let me see, 2, 2, and this is GZ is 3, 3. I think this is 2, 2. Sorry about this. 2, 2, 2, and it's 2, and this is 3, 3, and we can 3, 3, can say just 3. And then the important thing is we are going to this way. 1, 2, 3, then this way. So YZ is 4, and by the xt is 5, xy is 6. For this way. 1, 2, 3, 4, 5, 6. It is very important when we study the high order tensors. It's very complicated. It's a kind of the promise in the mathematics or mechanical engineering society. So it is, or mechanical properties societies. So we can say 1, 2, 3, 4, 5, 6. Then we can make it simple. We can simplify the stress like 1, 2, 3, 4, 5, 6. And also we assume this is exactly the same. So 1, 2, 3, 4, 5, 6. And then on 1, 2, 3, 4, 5, 6. In case of string. At the time we use 1, 2, 3, epsilon 4, 2, 5, the string 5 over 2, string 6 over 2, because it is related to the displacement of 2, 3, displacement 1, 3, and displacement 1, 2. So we can say it is over 2 over 2 over 2 over 2, half of the strain 2, 3, half of the strain 1, 3. 2 times of epsilon 4 is 2 times of the strain 2, 3. Do you understand? This is kind of the promise. So when you read the kinds of the papers or when you see some of the documents, not many guys, but some big guys, they really like use the tensor, and then they use a very high order tensors. So what is if they didn't simplify the metrics, the tensors, but is a lot of the papers should be used to calculate there's studies or researches. So they simplify the tensors and then notations, and then they can decrease the kinds of the there's writing, I think. Then they simplify and they can easily calculate any other stress or strain properties. Okay. Do you have any question? Okay. Okay. Today's lecture is done, and then I'm going to study the next. I'm going to study the analytic term in the next lectures. Now, I think I didn't upload the next lectures. I think I will upload it today, and then we're going to study the energetics the next lectures. Okay, thanks a lot. And then I'm sorry to wait. I have the connection problem. And then I will okay, and then I will keep the exam date. Then yeah, and then the topic selection due is this Thursday, and then I will send the paper to students didn't select. I will send the papers, select papers, and they're gonna use the paper that I sent, and then prepare the presentation. One more thing is, since you have only 7 minutes for the presentations, please don't make a lot of the slide. Just in my case, I only spend 1 minute for one slide. So it means you don't need to make over 10 pages or 11, 20 pages. Just in my case, the 7 presentation time is only 7 slides is enough, I think. So don't spend lots of time and then just show how to calculate it, how to build the most circles using the paper's work. Okay, thanks a lot.
Thank
Do you
you.
have any question? Yeah. Okay, thank you.
Thank you.